Hello everyone, this is the second lecture of week 7. So, we were learning about constraint optimization algorithms. So, in the last lecture I briefly gave a recap of what constraint optimization is and the classification of constraint optimization into linear and non-linear. And we began with discussing how an algorithm can be framed for solving a nonlinear optimization problem, right. So, if you recall, we started with a function q tilde of x, which is f of x when x belongs to the constraint set and infinity when x does not belong to the constraint set. Okay. So, this is perfectly equivalent to what we want to solve, but there is a problem that q tilde of x is not smooth, okay, not differentiable, right. So, how to make it differentiable? So, I am now defining a slightly different function q of x, and what is that? So, that will be before that let me actually consider this particular problem, consider minimizing f of x subject to the condition that we will say h of x equal to 0. Okay. So, what does this mean? It means that so in this we only have one equality constraint, but and no inequality constraint, m is equal to 1 and p equal to 0. Okay. So, let us consider the simple problem and then we will try to first frame an algorithm for this. We will extend that to the general setting a little later. Okay. So, for this problem I am going to define q of x as f of x plus gamma into h of x the whole squared. Okay. So, I will actually write this as q of x comma gamma, because it also depends on this variable gamma. Okay. So, what is the physical meaning of this particular function? So, you can see that this satisfies this particular constraint that when x belongs to the set, the constraint set S, q of x comma gamma is just f of x itself. Okay. But when x not in S, this does not satisfy infinity. Okay. So, in that case it is actually different from it is just f of x plus gamma into h squared of x. Okay. So, the gamma that you have here is some non-negative quantity called as the penalty parameter, and gamma h of x squared is actually called the penalty function. So, here it is the quadratic function, right. So, this is denoted as the penalty function. So, what we are saying is that q of x comma lambda is f of x if as long as x is in the constraint set. Okay. So, but when you move out of the constraint set, okay, based on how close you are to the constraint set, this function actually levies a penalty. Okay. So, the farther you are from the constraint set, larger is the penalty that you face. Okay. So, again to understand this geometrically, okay. So, I will try to explain this as such. I mean this could be difficult. Okay. So, consider that consider this particular problem that we considered in the last class, minimize x1 plus x2 subject to the constraint that x1 squared plus x2 squared equal to 1, right. So, in that case you have a circle which is the constraint set, the boundary of the circle is the constraint set. Okay. So, on the constraint set it is just f of x whatever it is, okay. But outside the constraint set, that is it could be inside the circle or outside the circle, but not on the boundary. Okay. So, you are not just having f of x, but you have f of x plus a penalty. Okay. So, if you look at what is happening outside the circle, okay. So, it is not just a simple x plus y, it is x plus y plus a penalty. So, the penalty is getting added here, 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 everywhere. Okay. So, ideally we would have wanted the penalty to be infinity. Okay. So, if for example, gamma were equal to infinity. So, I just put gamma greater than 0, right. So, instead if I had put gamma equal to infinity, right. So, then this function is exactly equal to q tilde of x, right. That is, so I can write it like this: limit gamma tends to infinity, q of x gamma is actually q tilde of x, right. So, for very high values of gamma, you can see that q of x comma gamma is approaching q tilde of x. Okay. So, fine, but I mean what is so great if you are actually not minimizing q tilde of x. If you are minimizing q tilde of x, we are actually solving the problem, but if you are only minimizing q of x comma lambda, which only approaches q tilde of x as gamma tends to infinity. So, you might ask what is the use, right. So, the use is that q of x comma gamma that we have considered here is actually a differentiable function. Okay. So, yeah, for any given gamma, of course, not when gamma is infinity, but yeah, for any positive gamma, however large it is, okay, you can see that q of x comma gamma is differentiable, twice differentiable also, because we assume that f, g I, h j's, they are all twice differentiable, right. So, q of x comma gamma is twice differentiable. Okay. So, I mean if you are looking at the situation here, it means that we have, so this is not true. I mean min x in S is f of x is not equivalent to min x in R n q of x comma gamma. So, this is not true, okay. But given that q of x comma gamma is going to q tilde of x as gamma tends to infinity, it turns out that for high values of gamma you get close enough to the minimum of f of x. Okay. So, that is the reason why we can actually substitute a constrained optimization problem with an unconstrained optimization problem, where you are actually minimizing a quadratic penalty function. So, this function q of x comma gamma is actually called as quadratic penalty function of the given constrained optimization problem. Okay. So, the method that minimizes this particular function is called as the quadratic penalty method. Okay. So, that is the first method that we are going to learn in detail. Okay. So, the method is as follows. Okay. So, consider a positive increasing sequence gamma 1, or maybe we will start with gamma 0, gamma 0, gamma 1, gamma 2 dot dot dot, such that gamma n tends to infinity. Of course, it must diverge to infinity. Okay. So, in the first step, let x 0 be the unconstrained minimum of q of x comma gamma 0. Okay. Okay. So, you are minimizing instead of minimizing f of x, okay, you are minimizing q of x comma gamma 0. Okay. So, that is the so I will put it as gamma 0, yeah, first step. Okay. Of course, I mean this need not give the right answer, that is it need not be the minimum of x when x belongs to S. Okay. So, I mean this is not somewhere we are going to stop. So, I mean we can try x 1 which is minimizing q of x comma gamma 1. Okay. We can try x 2 which is the minimizer of q of x comma gamma 2, x 3 is minimizer of q of x comma gamma 3 and so on. Okay. We can continue this and stop when the minimum q of x k comma gamma k is actually very close to f of x k. Okay. So, to clarify this, so yeah, so find the minimizer x naught using any algorithm for unconstrained optimization. Okay. And verify if q of x naught gamma naught is very close to f of x naught. Okay. So, what does it mean if q of x naught gamma naught is very close to f of x naught, given that q of x comma gamma is f of x plus gamma of h of x the whole squared, gamma into h of x the whole squared. It means that gamma into h of x the whole squared is so close to 0, right. That means the penalty function what you are considering h of x is actually very close to 0, right. That means the point that you are considering is actually very close to the constraint set, because the constraint set satisfies h of x equal to 0. Okay. So, h of x the whole squared, if it is very close to 0, that means x is very close to the constraint set. Okay. So, yeah, if the condition is satisfied, you stop. I mean if q of x naught gamma naught is very close to f of x naught, then you stop. Okay. So, if not, then yeah, you go to the next step, find x 1, okay, this is x 1, yeah, find x 1 using any algo for unconstrained optimization. Okay. So, now again verify if q of x 1 gamma 1 is approximately equal to f of x 1. Okay. So, yeah, this can be continued until you actually get q of x k gamma k is approximately equal to f of x k. Okay. So, yeah, the algorithm for quadratic penalty method is as follows. So, in the first step, initialize x naught k equal to 0 and yeah, a tolerance, and yeah, the sequence gamma naught, gamma 1, gamma 2 dot dot dot. Yeah, this must be an increasing sequence, that means gamma 0 less than gamma 1 less than gamma 2 dot dot dot. Okay. It must be positive, gamma naught itself must be greater than 0 and it must be tending to infinity. Okay. So, remember all those conditions that we have written here. Yeah. So, this is the condition. So, while q of x k gamma k minus f of x k greater than tolerance. So, yeah, find x k which is min x in R n q of x comma gamma k, okay, and yeah, put k equal to k plus 1 and yes, I think that should be fine. Now, yeah, so when this is satisfied, you come out of the loop and you output x k as the minimizer. Okay, so this is roughly the algorithm. Note that this line that find x k which is the so I should have written actually argmin because yeah, so this is actually the minimizer and not the minimum, right. So, I should write argmin yeah x in R n. Okay. So, this step whatever I have written here is, I mean I have just written it in one line, but it actually needs a complete algorithm, right. I mean, so you have to use one of the algorithms that we have learned, either the gradient descent method or conjugate gradient method or the Newton's method, one of these methods you have to use, so that we find the minimizer of this unconstrained optimization problem. Okay. So, this is roughly the no, this is exactly the quadratic penalty method algorithm. Okay. So, we will now indicate how we actually code this in Python. Okay. So, yeah, you can recall the codes that we used for all unconstrained optimization algorithms here. So, yeah, it's quite long. We have used many of the space here. Okay. So, we will now move to a new tab in Google Colab. Okay. And yeah, so we are going to start with a quadratic penalty method for a problem with one equality constraint. Okay. So, I can possibly write down that this is quadratic penalty method for one equality constraint. Okay. Fine. So, yeah, we will start with importing numpy and we will define f of x, which is x. So, I mean we can work for the same problem x 1 plus x 2 subject to the condition that x 1 squared plus x 2 squared equal to 1. So, q of x comma gamma, so gamma is what I am representing as gm here. Okay. So, that is going to be f of x plus gamma into x of 0 squared plus x of 1 squared minus 1 the whole squared, and so since we want to use one of the algorithms for the unconstrained optimization, right. So, let us define the gradient function. We will also define the Hessian to, so that we can use the Newton's method. Okay. So, return del f of x is 1 comma 1, and so here we will have two into gamma into yeah. So, this is common. So, let me possibly write it here, 2 into gamma into x of 0 squared plus x of 1 squared minus 1, okay. And yeah. So, within this we will have okay, I mean no, this need not be common. Okay. So, okay, I think let us do it from the beginning, I am sorry. Okay. So, if we differentiate gamma into x 1 squared plus x 2 squared minus 1 the whole squared, right. So, if you differentiate with respect to x 1, that is x of 0, you will get yeah. So, 2 into g m into x of 0 plus no 2 into g m into okay. So, yeah, you will get this fully x of 0 the whole squared plus x of 1 the whole squared minus 1, and then we differentiate this to get 2 into x of 0, right. So, that is the first component, and the second component is the same thing into 2 into x of 1. Okay. So, yeah, I can write it like this. Yeah. So, yeah, this is just I can write this as 4 into. Okay. So, by differentiating this I got 1 comma 1. By differentiating this I am getting 4 gamma into x of 0 the whole squared plus x of 1 the whole squared minus 1 into x of 0 comma x of 1, okay. And okay. So, now we will write down the Hessian, okay. So, this the Hessian is 0, for this the Hessian is 0, but for this it will be a little more complicated, okay. So, we will have yeah. So, the component 0 comma 0 will be so you have the product of x of 0 and this quantity, right. So, if you just take x of 0, that is 1. So, you will have 4 into gamma into x of 0 squared plus x of 1 squared minus 1 plus so, yeah, now when you differentiate this you have 2 x of 0. So, you will have 8 gamma x of 0 squared, okay. So, this is 0 0. Now, for 0 1 you will only have this component. So, that is 8 gamma x of 0 x of 1, sorry, 8 gamma x of 0 x of 1, okay. Oh, okay. So, that is the first row, and the second row will be yeah, a copy of this, but in a slightly different way. It is 8 gamma x of 0 x of 1, that is fine, but yeah, this is going to be 4 gamma into x of 0 squared plus x of 1 squared minus 1 plus 8 into gamma into x of 1 squared, okay. So, I have defined q, I have defined the gradient, I have defined the Hessian, okay. Now, we will move to the code. So, let me just define a starting point So, let us say -1 comma -1, okay. And let me start with some value of gamma which is 1, okay. So, if you recall the code, yeah, we initialized x 0, we have k equal to 0 can be initialized, and yeah, tolerance we will initialize that as 1 e minus 6, and this sequence gamma 0, gamma 1, gamma 2 and so on, we will initialize gamma 0 as 1, gamma 1 as 2, gamma 2 as 4 and so on, okay. So, in other words, we are actually so recall that we are considering this problem of minimizing x 1 plus x 2 subject to x 1 squared plus x 2 squared equal to 1, okay. So, let us start with -1 yeah, of course, k is equal to 0, we will put tolerance equal to 1 e minus 6, and so gamma 0 is 1, gamma 1 is 2, gamma 2 is 4, and gamma k is 2 gamma k minus 1. Okay. So, this is obviously an increasing sequence and it goes to infinity, right. So, let us do this. Okay. So, of course, I have started with gamma equal to 1, I will also put okay, yeah. So, now if you recall, the stopping condition is that q of x comma gamma minus f of x must be greater than the tolerance. Okay, the tolerance is 1 e minus 6, I will just represent this as 1 e minus 6. Okay. And here I need to solve an unconstrained optimization problem, right. So, for that let me in this case use Newton's method. Okay. So, while if you recall what Newton's method is, so you just try grad of x comma g m greater than 1 e minus 6 again, okay. X equal to x minus np dot lineal dot in of h of x comma g m at grad of x comma g m. So, I have just done h inverse of x matrix multiplied with delta delta q of x, okay. So, that is okay, and yeah, so maybe you can print the values in the inner loop, so that so yeah where you will have x of 0, x of 1 and the norm of grad of x comma gamma, and so this is the inner loop. So, in the outer loop you can possibly first print gamma, that is going to be an integer, right, a positive integer. The rest of the things are going to be the same. So, yeah, this is going to differ, but I think I can copy here, just that here I should change it as np dot abs of q of x comma g m minus f of x. Okay. Yeah, and of course, you need to multiply your gamma by 2. So, yeah, this is the this is roughly the code. Okay. Fine. So, let us run this algorithm. I think there was an error that I fixed for defining the Hessian matrix. I needed to write return. Okay. So, code. Okay. So, I should have given gamma here. So, that is another error that I had. I mean, for percentage d I should have included gamma. So, let us check if it is going fine. Okay. Yeah. So, this is the answer. You have So, when gamma is 262,144, that is 2.6 into 10 power 5. Okay. So, I mean you could have recognized that this is 2 power 18. Okay. The answer is minus 1 by root 2 minus 1 by root 2, and yeah, the norm is less than 1 u minus 6. Okay. So, yeah, after 19 iterations, so this is the 19th iteration, right. So, you can see that yeah, we started with gamma equal to 1, that is gamma 0 equal to 1, gamma 1 was equal to 2, gamma 2 was equal to 3, sorry, gamma 2 was equal to 4, gamma 3 was gamma 4 was equal to 8, and so on. Okay. So, gamma k is 2 power k minus 1. Okay. So, the gamma value kept on doubling, and when gamma was yeah 2 power 18, that is for gamma 19, right. So, we have got the right answer, and whatever you get inside is the result of the inner loop that you have here, okay, where we actually use Newton's method to solve each of the optimization problem. We have implemented quadratic penalty method algorithm for this particular problem. So, for more complicated problems where you have, let us say, many equality constraints or inequality constraints, yeah, what needs to be done, we will actually learn in the next